Hello everyone, this is Jason Chin from Oricon. Welcome to our GED talk. In this presentation, we will compare two point cloud data acquisition methodology, terrestrial laser scanning, and structure from motion photogrammetry. And at the end, we will discuss the digital tunnel mapping result based on our site trials. And then, we will recommend a method for digital mapping in tunnels based on our experience and discuss the advantage of our future development of digital tunnel mapping. So these are the three trials that we carry out our trials. The trials were conducted in two drill and blast hard rock tunnels in Hong Kong. Trial 1 and 2 were carried out in Tunnel A and Trial 3 in Tunnel B. In Trial 1 and 2, the tunnel face is driven in Grade 1, Grade 2, 3 granite, and for Trial 3, the tunnel face is situated in Grade 2 fine ash tuff. Based on the observation on site, the rock mass overall becomes poorer and blockier from Trial 1 to Trial 3, and this is also consistent with the factor of RQD over JN, which describes the degree of jointing or block size of the rock mass. And with my introduction, I now pass the presentation to my colleague Philip Wu. Thank you.
Thank you, Jason. In the site trial, two remote sensing techniques, terrestrial laser scanning and structure from motion photogrammetry, were used to generate point clouds for the exposed subwall tunnel surface. The laser scanning were carried out by Leica PLK360 imaging laser scanner, which can produce color laser point cloud. In the site trials, two laser scans were taken at different positions at approximately 10 to 15 meters away from the tunnel face. For photogrammetry, the photos were taken by a 24 megapixel full-frame mirrorless camera equipped with a 24mm f1.8 prime lens and a tripod. The photos were taken at approximately 15 meters from the tunnel face. Each photo was taken at a different location, with at least 60% overlap with prior photo. Based on our trials for creating point cloud using photogrammetry successfully, the experiences we would like to highlight and share with you are, first of all, better to use a wide-angle prime lens. Second, use higher f-number to avoid shallow depth of field. Thirdly, use consistent camera setting, so avoid to use automatic mode. Last but not least, because of higher f-number, longer exposure is required, so good light source and tripod is a must. For the result, we did a number of comparisons. For laser scanning and photogrammetry, the resolution is similar. Both can achieve up to 5 mm. Compared with the survey points on the excavation profiles measured using typical survey method with a total station, although laser scanning can achieve high accuracy, the point cloud generated by photogrammetry is considered sufficient for tunnel digital mapping. In terms of visualization, the point cloud data generated by the photogrammetry have more vibrant colors, which can help geologists to better visually identify possible features on the tunnel faces. For photogrammetry, we did a comparison between the point cloud generated by 10 photos and up to 58 photos. As shown in the table, the accuracy of point clouds built from 10 photos are indeed lower. However, when the number of photos was reduced to 10, occlusion problem means the areas of missing point cloud data does not worsen significantly. And the texture of the rock surfaces is also almost unaffected. The point clouds were then tested for semi-automatic extraction of rock mass discontinuity using DRM 2.0, which is an Oricon in-house developed software, and PHASES, which is a free software. In general, the digital mapping results are found to be in good agreement with the manual mapping in Trial 2 and 3, and to a lesser extent in Trial 1. In the massive rock mass in Trial 1, the major joint sets cannot be effectively classified among the data with high noise ratio shown in the stereo plot, which is because not many rock joint surfaces are exposed, and also quite a lot of non-rock joint surfaces are identified, mainly the blasting or breaking induced fracture surfaces. Overall, the results are consistent in that, as the rock mass become blockier with lower RQD and higher JN from Trial 1 to Trial 3. The number of identified planes increases with increasing accuracy. Okay, now I will pass the floor back to Jason.
Thank you, Philip. As shown before, although the accuracy of photogrammetry is lower, it is considered sufficient for tunnel mapping. And in addition, based on our experience, the time required for data acquisition, processing, and interpretation of laser scanning and photogrammetry is actually similar. And one very important point is, compared with laser scanning, the cost of photogrammetry is much lower. Therefore, from our point of view, photogrammetry is a preferable data acquisition method for tunnel digital mapping based on the common tunnel excavation practice in Hong Kong. Although digital rock mapping cannot replace traditional tunnel mapping at this stage due to challenges such as joint roughness and fillings, the technique can supplement traditional tunnel mapping by providing massive objective and consistent data in limited time frame before the tunnel support is being installed. It can also help to carry out detailed statistical study to build up useful discrete fraction network database for underground development and bring other advantages. In addition, this technique is being continuously refined and Oricon is exploring to improve this technique, such as we are exploring ways for continuity trace and block extraction. And we believe that digital tunnel mapping will become more useful and popular in the near future.
With that, we conclude our GED talk. Thank you.